This chapter 7.6, the energy storage in inductor. When we study a capacitor, we discussed about the energy storage in the capacitor. In the same way, we will deal with about the inductor energy. As you see, in the case of capacitor, the energy in the inductor is the same. The energy is this is integral of power. So energy means the integral of the power according to the time. So before we discuss about the energy, we need to know about the power is V and I in electric system. So in the case of an inductor, we define this is a voltage FEL and current is IL. We use the passive convention. Then the relationship between the current and voltage is also like that. VL is L dt IL. There is an inductor equation. So we can substitute the voltage here is these values. So insert here the V dt di and I is a power in the inductor. So when the current is following here, then the power is looks like that. We need to think about the more in detail about the characteristic of an inductor. So because this is the inductor equation. Inductor equation show us all of the characteristics of an inductor. So if the current is 10 ampere for time to 0 to 10 seconds, then what happens when the V according to the in two terminals of inductor? Because in this area, in this period, t is 0 and 10 seconds, then current is same values, 10 ampere. So for this period, the VL, how much is it? Because VL is L dt di and current is L dt d 10. This is a known variation according to time. So that value is 0. So that means 0. So this is 0. So we need to calculate the power here. Then what happened to the power? In this area, the power is VI. Because the voltage is 0. So for this period, the power value is 0. And current is 10 ampere. So what's the meaning of here? That means for this period, inductor current flowing to 10 ampere. That means the energy stored in the inductor is constant. The energy stored in the inductor is proportional to the current is 10 ampere. That means 10 amperes the energy is stored in this inductor and no variation. It means the energy is constant, no charging or no discharging. So because inductor is stored energy by the current, that means actually the inductor stored energy is a magnetic field, but the magnetic field is proportional to the current. So that means the current is constant. That means there are no variation of charged energy in the inductor. So this is that if voltage is toward, occurs to the inductor voltage is some values, then we will redraw here. So in the case for the VL is 1 volt for time to 0 to 10 seconds, and inductor is 1 Henry. Actually 1 Henry is a very huge values in real practical the inductance. Anyway, to simple calculation we choose the 1 Henry. Then what happened? 0 10 seconds is time. Second, the V is 1. Then what's the matter? What happened in the current? But we need to know about the T0, 10 ampere. And what happened here? Actually, no, so sorry. We will use 0.1 ampere. No, sorry. We L is not 0.1 Henry to make a simple calculation. And initial value here at this time is 10 ampere here. Then for this period, the voltage is L dTdI. Oh, I'm sorry. I'm sorry. To the simple calculation, we choose. I'm sorry. Yeah, it's a 10 Henry, and this is more simple. I'm sorry. Then what happened here? Because V is for this period 0 to 10, that is very one volt is 10 dTdI. So what's the meaning of here? The dTdI is 0.1. So the ratio is increasing the current is 0.1 ampere per second. So that means for 1 second the current increase 0.1 ampere. Then what happened in the 10 second? Because that value is constant. So for 10 seconds it will increase to the, how much is it? 11 ampere. Then what happened? The power over here. Power over here. Because this is at first this is a 10 because 10 and 1. But in this case, how much is it? 11 here. So anyway, power is here, is the here, that means. Then stored energy for this period is integral over here. So it will be increased about in this way form. Oh, sorry, that will be in this here. So this area will be, this is 10, and area is 10.5 multiplied by 10 is 10.5. 105. The unit of this is joule. This is total energy for this period. That means for 10 seconds, the inductor stored energy is 105 joule here. So this is the way. So this is a simple example to describe the energy stored in inductor for the constant current condition or the constant voltage condition here. The constant is constant, I mean the current is constant, that means there are no voltage between the inductor. That means no power occurs to the inductor. That means no energy storage variation. But there are some voltage between the inductor. That means some current will vary. If voltage is positive, then current is increased. That means the stored energy will be increased because the current is increased. Otherwise, if the voltage is negative, that means the current going through this inductor is reduced. So that means the power is discharged from the inductor to the load. So anyway, this is a power inductor. So we will think about it more simply by equation. P is VI, that means L dTd I and I. So to calculate the energy, then we have to do something here. T0 to D, the P, d tau. So I think T0 to T, that is, what's the meaning here? The stored energy from T0 to T. That is the meaning of here. Meaning of this is here. So that is P is that values L D D I. Actually, this is T. L I D tau. Then we can eliminate here. So I T0 IT L I D I. So they're transferred to L I tau T0 T. So T square here. So if energy stored T0 is 0, that means energy stored for the inductor is so when you discuss about this is capacitor, this is inductor, and this is the voltage VC and current IC and capacitance, and this is VL and current IL, then this is L. Then stored energy is half C VC square. But in the case of inductor, energy stored inductor is half L current square. So you need to familiar with this equation. So power is capacitor, that was here, but inductor is case here. The unit of this is a joule. So this is an example for the find current inductor. It's a very simple problem, so we'll do it here. Okay. This is an example 761. So we need to find the current in the inductor when the inductance is 0.1 Henry. Actually, 0.1 Henry is very huge values. So in simple way, the inductance should be like so this is just the value to use in simple calculation. And generally, when you use inductance in the real practical, the circuit may be about 1 millihenry or several microhenry. That's enough. So anyway, we will find the current here, but in the problem, the voltage occurs to the inductor is given in this way here. Here, this looks complicated maybe. So the graph of this voltage looks like here, this waveform here, then right here. So we need to define the current here. It's very simple. It's not easy. Oh, no, sorry. It's easy. Very easy. It's not complicated. Because we need to know about the current. This is a given value of the initial value of current. So what is the relationship between the inductor, the current and voltage in the inductor? VL is L dt di. So I'll use it here. So V is L dt di. In the problem, voltage is 10 T E. It looks like here. So from the problem, we can get the dt di is 1 over L 10 T e minus 5T. Because inductance E is 0.1, so this is 100 T. That's it. So what should we do to get the current? We need to integral in the both side. So integral, let's say di from the 0 to t, that will be integral 0 to t 100 tau e minus 5 tau d tau. There will be current t is integral 0 to t 100 tau d tau. So to calculate here, you need to know a simple the equations. And what should we do? You know, the tau e. How about this? This is okay. Right, and minus 5 tau e minus 5 tau. So that value tau e minus 5 tau is 1 over 5 e minus 5 tau minus 1 over 5 dt d tau minus 5 tau. Oh, this is tau. So we integral both sides here. It's integral 5 that's it. So that value is minus 1 over 25. This is 0 and t, and minus 5 tau zero t. So that will be, how much is it? It's because this is 0. So we somewhere here, this is common. It is common. So minus 25 e minus 5 tau. So 1 plus 5 tau. So because that is here, so we insert that into there. So we calculate here is 100 minus 25e minus 5 tau 1 plus 5 tau 0 to t. So there will be 100 minus tau minus 5t. Actually, this is t. E minus 5t. And when it's 0, then it's eliminated. So there'll be 25 here. So that value is 4. That value is here 1 minus 5t, 1 plus 5t here. This is a current equation about here. So that looks like it is here. We went to the module here because these are positive values. Among of these values will increase the current in this here. So the equation is written in this way. So problem is simple, but because of this interval, it looks more complicated. From now, you solve some problems, but the burden to solve the equation, the circuit, is to solve the equation such like that. You have to integral or we have to solve differential equations. Then the integral would be some complicated. But this is covered in high school or in your freshman. You learn in the fundamental mathematical subject. From there, I hope you will be familiar with these cases. So when you meet some problems just like that, I will give you the derivation of these equations, but you need to study them here in your previous books on here. Okay. Then this is another example. Is to find the power energy for inductor. They give the current way here. We solve these problems. Okay. Maybe like excuse me. Is the problem? Okay. This is the problem requires the power to find the power and the energy for the inductor. It's not a complicated problem. It's simple. It's not difficult. Okay. Because we know to get the power and the energy, we need to know the voltage here first. So we'll find the voltage first. So if we draw the voltage here, 1 second, 2 seconds, this is a V, this is a V. Then because the current looks like here, the current is 0 when t is here, or current is 20t for t 20 and constant 20 for excuse me, this is not 20, this is 1 second. This is 1 and 1 to t is 20. Then we need to know the voltage. How do we know that? Because V is L dt di. So because inductance is here 0.1, so 0.1 dt di here. So when t is the V is 0, then 0.1 dt 0 is 0, so that is 0. For 0 to 1, because it's 20, so 0.1 dTAD 20T is 2. So that value is 2. And from 1 second, then the V is 0.1 dTD 20. This is constant because of this 0, so that will be 0. So that will be 0. So we can draw the voltage values here is when it is smaller than 0, so it will be 0. And for this area from 1 to 1, from 0 to 1, that value is, for example, constant value 2. In after 1 second, this is a 0. So so this will be a result of here. Then we need to calculate the power. So what should we do? Then power is VI. Here, the power is VI. So what should we do? Then we need to calculate the here. P is 4, T is 0 here, whereas the V is 0, and current is 0, so it will be 0. Then 1 from 1 to, 0 to 1. Then V is 2, and current is 20T, so 40T. And from 1 second, there will be voltage is 0 and current is 20, so that will be 0. So we can draw the power here. 1, 2, and this is power P. So that value is 0, and from here we increase here about, because this is 1, that will be 40, and here is 0 here. And then how about the energy here? The energy is integral T0 T P dt. So if there are, before the 1 second, 0 second, when T is smaller than 0, because their current is 0 here, there is no stored energy in the inductor. So we can say here is because this is 0. Why? The power is 0. From 0 to T, 0 to 1, then that value is 0 to T, power is 40 tau d tau. So that will be 20 tau square 0 to T. So that is 20T square. And after that, when T is, from the 1, because the power is 0, so no variation of the energy. So that in this case, the energy at T is 1 plus integral 1 to T, the power is 0 d tau. So they are the same with T energy is 1, that means 20. So that will be 20. So we rewrite energy here is 0 when t is smaller than 0, 20t squared 1 and 20 here. So we can go here 1, 2, this is energy, and it is joule. There will be 0, and 1 second there will be 20, but increase like in the second order waveform, then it will be constant here. And that's a waveform of the current and voltage and power and energy this way. This is another example over here. So to find the power and energy from the inductor here, it looks more complicated, but it's not difficult because we know already the equation of the inductance. We get here, we want to know the relationship between the current and voltage, then we should use that. That's it. So because t is time is from the 0 second, then this is satisfied. So for t is t from the 0, then v is L dt di. The v is here because it's here, current is here because of these conditions. So 2e exponential 1 minus 2t is L dt 20te here. So L is 0.1. And that's it. Then what should we do? We need to find the power. Then power, we calculate the power. Okay, eliminate this here. Then P is VI, and that's it. So this is 0 for t is smaller than 0. Why? Because of that. Then when t is from the 0, then V is here, and current is 20 t exponential here. Then we can make simple. That's a 40 and t and exponential. This minus 2t and minus 2t minus 40 1 minus 2t here. So all the unit over here is what? 4t larger than 0. Then what is the energy here? Energy. Because the current is 0, the before the t is 0. So the before the 0, the energy is 0. So we need to think about this content over here. There will be 1/2 Li squared. Then what's L? 0.1, and current is 20t squared. So 20 squared t squared is equal to minus 4t, and there will be 20 t squared is exponential minus 40. Unity is joule. Then t is larger than 0. So this is a simple way to calculate energy here. Next, we discuss about the series inductor or parallel inductor. This is the dual of the capacitor. Inductor's case is very similar with the resistor case. So first we discuss about the series inductor. If there are some series inductor here, and 1 and 2 and 3, then we need to make we'll make the same inductance here. For example, we have inductor here. It's 1, 2, blah blah. Here we define L1. This is L2. This is Ln. I mean there are n inductors here. Then this is the voltage flow. The terminal voltage here V. And this is the current I. Then we need to think about this is one inductor's voltage is V1 and define. Okay. We define this is V1, this is V2, and this is Vn. Our final goal is to find out now one inductor. Then this is V, this is current, and this is Ls. The Ls, which Ls we need to find out. When insert the n series inductor and one single inductor, then voltage is the same with here, then current is the same with each other. Then we can say VLs is the same with the series connected inductor. So our target is find out what is Ls. So to do that, we need to do right here, because the inductor is series connected here, so total voltage terminal here V is the same with all voltage over here. So we can write V is V1 plus V2 plus and Vn. Then we know about the characteristic of voltage and current over here. Because this inductor is connected in series way, so this current I1 is same with I1, I2, and IN, all the same with I. So V1 is L1 dTd I, because I is constant. Common, it's not constant. I is common in all inductors. Then V2 is L2 dD I2, and Vn is Ln dTd In. So we adding here. Then L1 dTd I plus L2 dTd I plus Ln dTd I. So dTdi is common. So this is L1 plus L2 plus Ln dTdi. So let me analyze this case. What is the relation between V and I and Ls? It's very simple. The V is Ls dTdi. So our target over here is make a same V and the same current. That means V is Ls dTdi is the same equation. So to do that, what should we do? That value is the same with Ls. So we can get the result. Ls is L1 plus L2 plus Ln. From 1 to n there. So our conclusion is equivalent inductor. Our conclusion is like here. The equivalent inductor for the series inductors is the sum of n inductors. we need to adding over here. It's like a register. In the case of the parallel, it's very similar with that. When we discuss over here more time. In the case of parallel, this is a voltage here. There one inductor here, inductor here, inductor here. This is Ln, this is L1, this is L2. In this case, current is different. This is I1, I2, IN. That will be the V, and that will be the current I. So our target is, what is our target? Our target is same circuit with voltage and inductor is L divided by P, then current I. So our target is to find out LP to satisfy V is same with their values, current is the same with their values. So from here we know that V is LP TTDI. Then to solve this problem here, actually because inductor is connected in parallel, but from here we calculate the current is not what V is. I is, this current is I1, I2 plus IN in this way here. Then what is the problem? Because we don't know the I1 and I2 and IN, but we know the inductor equation. What is that? V is L dTdI. From here, we calculate I as integral form of 1 of L integral T0T V tau d tau plus I T0. This is the initial value over here. Then using here, then what is I1? I1 will be 1 of L1 integral T0T V tau d tau plus I1 T0 here. And here, the voltage is common of it. This is that value is same. So V is common in all the inductors. Then in the case of second is L2 T0T V tau d tau plus 2. I20 means the initial current of this current here. So in the same way here is Ln T0T V tau d tau plus IN and 0. So because this is common of all equations, so that will be that value integral T0T V tau d tau plus now this is T0, this is T0. That means from here we also have the same equation here. How much is it? I will be 1 over LP integral T0T V tau d tau plus I T0 here. So from here we know that that is same with that, and that will be same in here. So the same with here. We can eliminate each other. So what's that? The equivalent inductance can be written is here. From here, what is LP? Is its inverse inductance, and summarize over here. And again, inverse. So that's a way to get here. You know, you remember here. This is R1, R2, Rn. Then what is the Req? Req is 1 over Rn, 1 over R2, 1 over Rn, and inverse. The same way, this is inductor, 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 and inductor. Then L1, L2, Ln, then Leq. So Leq is 1 over L1, 1 over L2, 1 over Ln, inverse. There's a way to calculate the equivalent inductance when the inductor is connected in parallel. So this is example of here. To find the equivalent inductance, it's very simple. This inductance, we can redraw this circuit here. 2 millihenry, and the branch here 5 millihenry and 20 millihenry. Then 3 millihenry is here. So V is the current here. Now what should we do? And at first we can make here simply. Then from here we calculate that because this is a parallel, so there will be 5 millimeters 0.0051 plus 20 millimeters 0.02 inverse here. So that is 5 1,000 and 2 20 1,000 inverse is maybe it will be 10 2,500. That will be here. So 0.004 Henry. So that means this is the same in 4 millihenry. Then 2 milli. Okay. Then 2 millihenry, 4 millihenry, and 3 millihenry. So Leq is 2, 4, 3 is 9 millihenry. Simple calculation. It's very simple. In the same way, we can solve the same problem. It's not difficult. You can redraw to get the equivalent inductance. We have a first 3 millihenry here. Then we have 42 here and here, 3 millihenry, 42 millihenry, and 4 millihenry. It's simple. Then we have one more branch here. It's a 5 millihenry. Now we need to make simplify because 3 millihenry and 4 millihenry connected in series. So this is the same way 7 millihenry. Then this branch looks like 42 and 7 is connected in parallel. So that will be, how much is it? This is 0.042, 1 over 0.042 plus 1 over 0.007 inverse. That is equivalent inductance here. So you can calculate here is 42 1000 plus 6000 inverse. And 42 7000 inverse will be 0.006. That means that is 6 millihenry. Then this branch and this branch is connected in series. So total value will be 3 millihenry plus 6 millihenry plus 5 millihenry. Why? This is connected in series. So the result is 14 millihenry. That's the way to calculate the series of parallel inductance. It's very simple. The inductor is very similar with the capacitor, and not capacitor is a resistor, the viewpoint of the connection. So we already discussed about here. To summarize, we need to remember here this table. In the case of resistor, it does not store the energy. It only consumes the energy. But in the case of we have this is a little confused here. I will change the position of here. The capacitor. This is more good. Okay. In the inductor case, this store the energy by magnetic field here. And in the case of capacitor, is stored the electric field. So because energy is stored in the current, so in the case of inductor, current is continuous. That means current cannot be changed by stepwise. But in the case of capacitor, the voltage is continuous because voltage is a stored energy here. So relation between the resistor and inductor and capacitor is here. The V is IR. In the case of inductor, V is L dTdI. In the case of C, I is C dTdV. So this is the integral form of each element here. So you need to familiar with this equation. I mean, this is a kind of Ohm's law. We'll later discuss about the new Ohm's law in the base of not resistor, but the impedance. Impedance is kind of more or large concept to describe the passive component, not only resistor but also the capacitor and the inductor. We will discuss about that in the next semester electric circuits second. But anyway, in the relation between the voltage and current in the case of R is like here, but and the inductor's case, and this is the capacitor case. So you need to familiar with this equation. It's very important.